Dr. Pianoda here. In today's video, we will discuss a number of problems in which molecular structure is determined from the spectral data, NMR data. The first question is about what informations are derivable from H1 NMR spectra. The answer is a plethora of structural informations like distribution of hydrogen in the molecule, their chemical environment, neighbors, relaxation, stereochemistry, exchangeability, hydrogen bonding, chemical kinetics, entropy studies, fast reaction kinetics, etc. For example, NMR spectra can distinguish between the isomers of C4H9Br and between the propionaldehyde and acetone isomers. So the technique is very, very important for chemists. Examples are illustrated here. Then butyl bromide, 4 signals, no doublet. Secondary butyl bromide, also 4 signals, 1 doublet. Tertiary butyl bromide, 1 signal, 1 split. Isobutyl bromide, 3 signals, 2 doublets. So in this way, we can use NMR spectroscopy to derive the structure. Second question reads like this: NMR solvents, CW NMR spectrometer, and Zeeman splitting. A number of degraded solvents are used in NMR. Dipyridochloroform, DNSOD6 being the most common used. CWNMR consists of the following parts: a powerful DC magnet, radio frequency transmitter, radio frequency recorder, sample tube with spinner, recorder, dedicated computer. However, the modern instruments are highly sophisticated pulse type instruments, very costly, very sophisticated. Zeeman splitting, in the absence of magnetic field, nuclear spin states are of equal energy, which is degenerate. The magnetic field removes degeneration. It creates gap between the two states. The energy states are listed over here as E plus half and E minus half. The separation between the energy states in the form of frequency is gamma Bz upon 2 pi or Gn Bn upon Bz upon h. The other question is regarding TQ pattern and regarding septic doublet pattern. The CH3-CH2 residue gives a TQ pattern, whereas CH3 twice CH residue gives doublet sextet pattern. Multiplicity of a peak is given by n plus 1 rule, where spin half nuclei are involved. When 2 groups are involved in splitting, the formula is 2n1i1 plus 1 multiplied by 2n2i2 plus 1, illustrated by the example of 1 3 chloro propane. The middle CH2 gives 9 lines. The terminal CH2 gives 3 lines each. How many carbon-13 NMR signals will appear in the broadband H1 decoupled spectra of the following compounds: isomeric dichlorobenzenes, phenolene, pyridine, cholesterol, neopentyl bromide, diethoxybutyl and decalene. The answers are given. These examples are very simple, and for practice purposes they are very important. Once you practice simple examples, in quite good number, you will be able to remember the formula, remember the concept, and do a lot of complicated problems. Listed here are some common delta ppm ranges for H1 and carbon-13. One is expected to remember this data. Question 6 is about solving structure of a compound from IR and NMR data. The IR data at 1722 per centimeter is for carbonyl group. PMR data, the spectrometer frequency is 89.56 megahertz. The spectrum shows 8 lines. The values of the shift in Hertz units are noted. The line intensities are noted. Delta ppm values of lines are noted. Then see how do we calculate delta ppm for peaks and how do we calculate the spectrum. Procedure is line 1 minus line 2 position 7.3 Hertz. Line 2 minus line 3 position 7.3 Hertz. Line 3 minus line 4 position 7.34 Hertz. It means this is a quartet of intensity 1:3:3:1 and coupling constant 7.31 Hertz. It means this quartet results from nearby C3. Likewise, lines 6, 7 and 8 correspond to 1:2:1 doublet, triplet. It means the compound has a CH3, CH2. And one peak is unsplit, very strong peak, indicates methyl. Thus we arrive at the structure of the molecule. How do we calculate chemical shift is illustrated here. Delta ppm is obtained by dividing the Hertz unit value with the spectrometer frequency. This compound is 2-butanone. Question 6. An organic compound analyzed for percent carbon, percent H, formula C4H6O. Its NMR spectrum shows 4 H1 signals, 4 C13 signals. It means the only possible structure is methyl propylenoate. Question 7. Indicate the type of H environment in glyoxal, propane diol, methyl cyclopropane, isomerized alcohols, 3-chlorotentane, neopentyl chloride. The data is listed here. Glyoxal 1 type, propane diol 2, cyclohexane 1 type, ethyl cyclopropane 5, 1-butanol 5 types, 2-butanol 5 types, isobutyl alcohol 4 types, tertiary butyl alcohol 2 types, 3-chlorotentane 3 types, neopentyl chloride 2 types. In this manner, NMR spectroscopy is very, very helpful and also easy to understand. Question 8. Formula is given C4H10O, PH1 NMR peaks. We have to find the structure. The only possible structure is diethyl ether. So we see, first we note down the number of signals, then we note down the splitting pattern, line intensity, and chemical shift values. These 3 informations are very helpful in identifying the compound. Question 9 is C3H79NO shows 3 signals at low temperature, 2 signals at room temperature. It means clear cut this is a case of effect of temperature. You see in dimethyl paranoid, 2 methyl group hydrogens are not equivalent at low temperature. due to restricted rotation. At room temperature, rotation is fast. The two methyls no longer remain non-identical. They become equivalent. Another similar case is that of N,N-dimethylamminopyridine. At low temperature, the two methyl groups are not equivalent with respect to the pyridine nitrogen. At room temperature, they become equivalent. Question 10. Types of NMR signals. The terminology we use is singlet, doublet, doublet or doublet, triplet, quartet, quintet, sextet, multiplet, etc. Question 11 reads that what is indicated by multiplet showing line intensity 1, 4, 6, 4, 1, quintet. It means the structural type is R, CH2, CH, Cl, CH2R. Question 12, 90 MHz spectrometer. Compound gives two signals. The chemical shifts are noted in Hertz unit, which is field dependent. Now, how do we derive the delta ppm values? We simply divide the separation in Hertz by instrument frequency. Thus, we get signal A, delta ppm 5.5, signal B, delta ppm 11.1. And when the frequency of instrument is increased, the separation between TMS and compound peak is also increased accordingly. In the older literature, NMR phenomenon was understood on the basis of Larmor precision. Under the influence of magnetic field, the nuclear magnet begins to precess about the axis. This is called Larmor precision. Larmor was a famous mathematician. The Larmor equation has been derived later. W is equal to gamma Bz. Gamma is magnetic Ionic ratio. Bz is magnetic field. Omega is the frequency, angular frequency. Calculation of magnetic Ionic ratio or fluorine. Just by putting the data, we obtain the gamma value. Similarly, calculation of magnetic Ionic ratio and G factor for phosphorus 31. The spin value is given, half magnetic moment is given, 1.1305 nuclear magneton. Simply by putting the values in equation, we get gamma value, we get G value. In the beginning, such calculations may appear to be a bit complicated, but they are not so. They are very simple and very much essential. Every student must practice these values, the names of the symbols, their values, their calculations. A few practice makes you perfect. Question 14. How to interpret the NMR data for ethyl bromide, 2 peaks, ethyl alcohol, 3 peaks. Both molecules have respectively 2 and 3 types of hydrogens. So we get that number of peaks. In ethanol, a very special point has to be noted. Exchange of OH between nearby OH groups, nearby molecules, known as chemical exchange, simplifies the spectrum. If a sample of super dry ethanol is used, the OH hydrogen absorbs as a triplet. But normal alcohol, the OH hydrogen absorbs as a singlet due to chemical exchange. We have covered many points. Now we would like to revise the points. The following points will be discussed one by one. First, introduction to nuclear magnetic resonance spectroscopy technique. Then about discovery of NMR by Purcell and Lodge. NMR experiment using CW NMR spectrometer Same this older one, which is easy to understand. Why we use TMS has been very nicely explained here. The line diagram, how the CW NMR spectrometer works. G1 is splitting on NMR spectrometer diagrammatically shown here. The scope of NMR, almost every property can be studied by NMR. Technique is very, very important, including MRI, used in medical science and medical diagnostics. Nuclear spin vector. All nuclei don't have spin. Some have spin and corresponding spin angular momentum. J. Topole gave some empirical rules to guess the nuclear spin value. Some examples are noted here. Effect of quadripolar nuclei on shape of NMR absorption lines. Quadripolar nuclei are used to study nuclear quadrupole resonance spectroscopy. Case of hydrogen atom, proton is spherical in shape, spin quantum number half. So in the presence of magnetic field, two spin states are allowed. Resolution of spin vector. Any vector can be resolved into how many components? Twice the quantum number plus 1. There are various types of nuclei. The resolution is shown by examples here. Digital data. Nuclear magnetic moment, it is proportional to spin vector. G factor for proton 5.585. Nuclear magneton 5.051 into 10 to the power minus 27 joule per Tesla. Nuclear magnetic moment, by putting the values of constants, we get the value of million as 2.44 into 10 to the power minus 26 joule per Tesla. For electron, we use other unit known as Bohr magneton, which is about 1,000 times larger than nuclear magneton. Magnetization vector. When no magnetic field is applied, M is 0. When field is applied, M is non-zero. Boltzmann equation of population distribution. The two spin states of hydrogen become non-equivalent in the presence of magnetic field, and their population can be delineated using Boltzmann equation number 5. Calculation of population difference. Just by putting the values of energy gap and KT, we get the population difference value. Interaction between external magnetic field and the nuclear spin vector. The formula is minus mu n B0 cos theta. Bohr-Einstein resonance condition. In terms of delta E, the value is gamma H cross Bz. In terms of frequency, it is gamma by 2 pi multiplied by B, magnetic field. NMR absorption. When the radiation frequency becomes equal to the energy gap, absorption takes place. These days, various NMR frequencies are used, beginning from 100 to 1200 megahertz. Accordingly, magnetic field has to be used. Both are proportional. The line diagram showing how nuclear spin states are created and what is the energy gap, what is G-man splitting is shown nicely in this diagram. Line diagram. Control number of signals, areas and splitting of peaks. NMR frequency formula is given above. The effectiveness of NMR technique depends on a phenomenon called chemical shift. The line diagram of delta squared is shown here. And delta ppm is calculated by the formula given in equation 8. Examples of ditetrabutylbenzene benzene, 2 signals, chloroethylene, 3 signals. How do we calculate the magnetic field if frequency is given? The formula is B equal to h nu upon G m nu. For a given magnetic field Bz, the NMR resonance frequency are 1H, 19F, 13C, and 31PR in the ratio 100, 94.1, 25.1, 30.5. Use of chemical shift reagents. In the olden times, these reagents were used. They used to spread the NMR spectra so that concealed peaks can be delineated. Nowadays, their use has been discarded. Again, Larmor precision has been shown diagrammatically. Some compounds formula are given, number of their peak positions are given. We have to find the structure. So the separation in Hertz has to be divided by the instrument frequency. Thus we get delta ppm value. By comparing the data with the table, we can help explain the structure of the compound. Delta ppm is used by this formula. Frequency of sample minus frequency of reference divided by frequency of instrument. Some examples of compounds showing one NMR peak are the following: methane, ethane, acetone, dimethyl ether, ditertiary ketone, cyclohexane, methyl etc. Some more examples showing one or more NMR peaks are shown here: C5H10O, 3-pentanone, diethyl ketone, ethyl. Another example, methyl 3, CH2CO, CH2C, methyl 3, 2 singlet, 2 pentanone, 1 singlet, 2 triplet, 1 multiplet. Thank you very much. Thank you, viewers. I have tried to make the material very simple. Simple examples have been taken for beginners. I hope if you practice this video 2 times, you will be able to understand the basic principles of NMR. Thank you very much.